Hi everyone, welcome to our presentation, Intuitive and Efficient Roof Modeling for Reconstruction and Synthesis. This is a collaborated work with Biao, Bojian, Jianqiang, Lubing, Max, and Peter. The problem we want to solve is to model a planar roof in an efficient way. For example, given an area image shown on the left, the goal is to reconstruct a 3D roof as shown on the right that is planar and consistent with the image. We can use some commercial software to solve this problem. Here we show the workflow of an expert using 3D Max to model a roof. The expert first adds some outline vertices to form a face. Then the expert cuts the faces and adds roof vertices to get a 2D roof with the same topology as shown in the image. Finally, the expert moves the vertices along the z-axis to construct a 3D roof. However, it is very hard to enforce the roof planarity by moving the vertices around and visually checking the planarity from different views. For example, if we look at the pink face, we can see that it is far from being planar numerically. This is another example of using SIGGRAPH to model roofs. The expert first specifies the roof topology by adding vertices and faces in 2D. Then the expert builds some roof beams, which are vertical planes, such that the rooftop planes can be placed on top of it. In SIGGRAPH, there is no simple way to construct a face from a set of non-planar points. Therefore, when the artist notices such a failure, he manually triangulates the rooftops to guarantee the planarity. In this case, although the roof planarity is enforced, additional roof complexity is introduced, which is not ideal. Using commercial software for roof construction is flexible, but this workflow relies on the modeling experience of an artist. Indeed, there is another solution for roof construction called street skeleton. This approach takes roof outline as input, then outputs a roof that is embedded in 2D. These methods formulate roof construction as a problem of determining how the blue planes stemming from the outline edges intersect with each other. The intersection colored in red would give a 3D planar roof. These types of methods are simple and can guarantee the planarity directly. However, they also have some disadvantages. For example, since the roof topology and the roof embedding are solved at the same time, the constructed roof can have topology that is inconsistent with the input image or that is undesirable. Here we show one such example. The expected roof only has 2 roof vertices colored in red, but the roof constructed by the street skeleton can lead to more than 10 roof vertices. Another limitation is that it cannot handle the case where a face contains multiple outline edges. This is because by assumption, there is an independent roof face stemming from each outline edge. Here is a short summary of the 2 types of solutions we just discussed. The commercial software can guarantee the expected roof topology. It also allows interactive editing and is robust to noisy input. However, it is not friendly for beginners and requires complicated operations for modeling. The street skeleton-based methods only takes a roof outline as input and can construct roofs in an automatic way. This is easy to use for users without modeling experience. However, these methods cannot guarantee the structure of the solved roof topology and do not fully support interactive editing. It is also sensitive to noisy input. In this work, we propose a new roof modeling approach which combines the advantages of both solutions. Our approach is significantly more efficient and intuitive than the general-purpose commercial software and is more powerful and expressive than the street skeleton-based methods. Our method takes a roof graph as input. We propose a simple but effective planarity energy. Minimizing this energy using a continuous solver would give us a planar 3D roof. In this work, we also propose different regularizers to construct roofs for different use cases. Let's first start with some notations to better clarify our problem. We use a connectivity graph to represent the topology of a roof. Specifically, we are given a set of nodes V and a list of faces F to show how nodes are connected to each other to form roof faces. To visualize such an abstract graph, we need to embed it in 2D or 3D. For example, we can assign the node Vi a 2D position, which gives us a 2D embedding of this roof graph. We can also assign each node a 3D position to get a graph embedding in 3D. In principle, any assignment for the node position would give us an embedding, but not all of them are useful or desirable in practice. Therefore, we define a 3D embedding of a roof graph to be valid if each 3D roof face is planar and the roof has non-zero height. We can also define that a 2D embedding is valid if there exists a valid 3D embedding such that its projection in xy plane is the same as a 2D embedding. So our goal is to find valid 2D or 3D embeddings for a given roof where its topology is specified by a graph. For a roof graph, we categorize its edges and nodes into two groups. For example, the edges that belong to a single face are called outline edges. They are the boundary edges of the roof and colored in yellow. The edges that are shared by two faces are called roof edges, and they are colored in blue. We then call the nodes lying on the outline edges the outline vertices, which are colored in yellow, and the other nodes colored in blue are called roof vertices. One advantage of using a graph to represent the roof topology is its flexibility. We can use either the primal graph or the dual graph to encode the topology. For example, on the left, we show a primal graph where each gray node represents a vertex on the roof, and the edges in dark gray shows a connectivity between two nodes. We can construct the dual graph as shown in the middle, where now each gray node represents a roof face, and the gray edges show the adjacency between faces. One can easily convert the primal graph to the dual graph and vice versa. For example, to construct the primal graph from the dual graph, we can first add an additional node to represent the outside region, which is colored in red. Then the dual of the dual graph would give us a primal graph. Therefore, we can either use the primal or the dual graph to represent the roof topology equivalently. Here are some observations to motivate our method. First, roofs with the same outline can have different styles, such as the four roofs shown here. As we discussed before, the straight skeleton methods cannot handle this case since they assume that only a single roof can be constructed from the input outline. Therefore, to handle this case, we also need the adjacency information to specify the roof topology to model different roof styles. Another observation is that roofs with the same outline and topology can have different embeddings. Here we show 6 different but valid embeddings for the roof with the same topology. This suggests that multiple valid solutions exist, and we need extra constraints to rule out undesirable embeddings. Recall that our goal is to find a valid roof embedding such that each roof face is planar. The question is how to measure the planarity of a roof face. We start with a set of 3D points colored in red shown on the left. We can see that these red points are not coplanar, which means there does not exist a plane such that all the red points lie on that plane. In this case, we can conclude that the covariance matrix of this set of points has full rank. The covariance matrix is defined on the top right, which is positive semi-definite matrix so that all of its eigenvalues are non-negative. Then we know that the smallest eigenvalue of the covariance matrix in this case is larger than 0. On the right, we show another set of points that are coplanar. In this case, the covariance matrix of the point set loses 1 degree of freedom. Observe that in this case, the smallest eigenvalue of the covariance matrix should be 0. From these two examples, we can see that for a point set X, the smallest eigenvalue of the covariance matrix gives a coplanarity metric. We can therefore use this planarity metric to formulate our roof construction problem. Specifically, we take a roof graph as input, and our goal is to assign a 3D position for each vertex such that each roof face is planar. The planarity energy is defined on the right, where we measure the coplanarity of the vertices on each face. As we mentioned before, there are multiple global minima for this planarity energy. We therefore add 2 constraints. The first is that we fix the roof outline to the input positions and only solve for the positions of the roof vertices. This helps to make sure that the optimized roof can be consistent with the input image. We also add a hard constraint that for an arbitrary roof vertex x star, its height is fixed to a predefined value h. This can help avoid trivial solution where all the roof vertices have zero height. Also, this parameter h allows us to control the overall height of the constructed roof as shown on the left bottom. One of the major advantages of our optimization-based formulation is its flexibility. Besides the planarity energy, we can also add extra regularizers to obtain more desirable results. For example, the user can specify the initial 2D locations of the roof vertices. However, the user input can be invalid or incomplete. In this case, we can add extra energy term to enforce the 2D projections of the roof vertices to be close to the user input. In this way, we can obtain a planar roof that is close to the user's hand-drawn sketches. When there is no user input, we can still adopt some aesthetic regularizers to guide the optimization process to some more desirable roof embeddings. We can define such regularizers on the roof edges. For example, consider the roof edge E of P colored in green. It is shared by these two faces that are colored in blue and orange. Each face contains an outline edge denoted as E of P1 and E of P2 respectively. In this case, it would be plausible to have E of P lying in the media axis, which means the distance between E of P and E of P1 should be equal to the distance between E of P and E of P2. We can easily formulate this energy as shown below. Here, D is a function measures the distance between two parallel vectors. Here's another example. For this yellow roof edge E of Q, we can similarly find its two adjacent faces, and the corresponding outline edges E of Q1 and E of Q2. In this case, it would be plausible to have E of Q being the bisector of the angle formed by the two outline edges. We can also formulate this energy shown below, where A is a function measures the angle between two vectors. We can therefore combine the aesthetic energies we discussed before with the planarity energy. For the yellow edges, we add regularizers to the angles formed by the roof edge and the corresponding outline edges. For the green edges, we add regularizers to the distance between the roof edge and the corresponding outline edges. Optimizing the combined energy can give a more desirable roof embedding even without any user input. We can also set the outline vertices as free variables for optimization. For example, here we show a pavilion where the outline vertices are not in the same height. We categorize the outline vertices into three groups with different colors as shown in the bottom. In practice, all the green outline vertices are supposed to have the same height, and so are the yellow outline vertices. We therefore add two extra regularizers to penalize the variance of the height of the green vertices and the yellow vertices respectively. Starting from a random embedding, we solve the problem with and without the extra regularizers, which is controlled by the parameter eta. We can see that when eta equals to 0, we do not add extra constraints to the outline vertices, and the optimized roof is valid with planarity error smaller than the threshold, but it looks irregular. If we set eta to 1, which means we hope the green vertices and the yellow vertices have a similar height, the optimized roof embedding is valid and also more aesthetically pleasing. Here we show some other examples of roofs with outline vertices in different height, where the input images are shown on the left. We highlight the outline vertices with non-zero height in red. Our method can model roofs with different styles. Here we show some roofs constructed from the reference image shown on the top. For example, we can approximate curved roofs with planar subfaces to construct the traditional Hakatolo in China. We can also model roofs with vertical facades such as a temple and model roofs with inner courtyards such as Nagoya Castle in Japan. We can also model roofs with outline edges in different heights. Here we show a qualitative comparison to the straight skeleton-based method. The top row shows the reference images. The second row shows our constructed roofs textured by the image. And the third row shows the topology of our constructed roofs. The fourth row shows the roofs constructed by the straight skeleton method, and we highlight the major inconsistencies in topology with the input image using red boxes. We then apply the weighted straight skeleton method to try to fix those inconsistencies by tuning the edge weights. The results are shown in the last row. The black box shows the errors that are introduced by the weighted straight skeleton. As a comparison, The roofs that are constructed using our method are more consistent with the input image and topologically right. Here we show some qualitative evaluations about the 16 roofs shown in the previous slide. We report the number of visual inconsistencies and compare the topology between the constructed roof and the expected roof shown in the image. We can see that our method is more expressive than the street skeleton-based methods. We also asked 2 experts to model these roofs in 3D Max and SketchUp. We report the validity and topological errors of the constructed roofs. We can see that the roofs constructed in 3D Max are not planar. The number of polygon faces in the roofs constructed using SketchUp is very low since the expert has to triangulate faces to enforce planarity. Our method uses quasi-Newton for optimization, which is efficient. For example, it takes less than 5 minutes to construct a roof with more than 50 vertices, while it takes half an hour for modeling in SketchUp. As a comparison, our method is much easier to use and our constructed roofs have simpler topology. One direct application of our method is interactive editing, which is not fully supported by street skeleton-based methods. Here we show how to use our method to correct topological errors in the roof constructed by the street skeleton. Our optimization-based formulation supports different operations, including moving a vertex or an edge, snapping an edge, merging 2 faces or splitting a face, or forcing 2 faces to be adjacent. On the right, we can see that our roof is more plausible than the one constructed using street skeleton. Please see the supplementary video for more demonstrations. We can also use our method to construct a roof image pair dataset with more than 3,000 buildings. The texture coordinates and face labels are also given. We believe this dataset can be helpful for different data-driven tasks, including roof synthesis, roof detection, and segmentation. You can find the dataset in GitHub. We use this dataset for roof synthesis from scratch, which consists of 2 important components. The first component is roof outline prediction, where we train a transformer network to construct roof outlines from scratch. Here are some example outlines generated by our transformer. The second component is face adjacency prediction, where we take the generated outlines as input and use graph convolutional networks to predict the probability of 2 faces being adjacent to each other. We then obtain a dual graph of the synthesized roof, where we can run our roof optimization method described before to get a valid embedding of the synthesized roof. Here we show some examples of the synthesized roofs. Since our network predicts the probability of the adjacency, this allows us to extract multiple dual graphs with the same outline. Therefore, we can also synthesize roofs with different styles but with the same outline. In summary, in this work, we study how to efficiently model and embed a roof in 3D. We propose to use a roof graph to represent the roof topology and embed the roof in 3D by optimizing the planarity energy with other user-defined regularizers. Our optimization-based method is more expressive than the street skeleton method and also more efficient than the commercial software. Our method also allows interactive editing, and we use it to construct an image roof pair dataset. In this paper, we also discuss how to use our method for roof synthesis. Our method also has some limitations. For example, our formulation cannot directly handle curved roofs, including stadiums and skyscrapers. We did not model roof textures during the synthesis, and we did not touch automatic roof reconstruction from images. In the future, we plan to investigate how to reconstruct roofs from images automatically. It would also be interesting to investigate practical constraints for roof fabricability and how to synthesize roof textures as well. Thanks for your attention, and you can find our code and data in GitHub.